Hello and welcome back, everybody. This is going to be our last video in the section of differential equation. So this is going to be, I guess, kind of like a closure to all of this stuff, fun stuff that we can do. We've been talking about differential equations, how to solve for them, how to apply them, and all that other stuff. And there was this one part of the video that I made a while back that says, when it comes to the amount of differential equations that you can solve for out there, if we were represented as, like, say, a big board, the amount of differential equations that you can solve for versus, like, say, the amount of differential equations that are out there, it's very, very minimal. You could probably solve for about, like, say, at best, and if you are like say a professional or whatever, if there's even such a thing, you'll probably be able to solve for, like, say, less than 1% of it. Okay, but the important thing is we're not trying to solve for these differential equations, but rather we want to be able to analyze it, so then that way we can translate what it means to somebody that it may not be taking calculus or may not be taking differential equation. So that's what this last section is about. We're going to look at something called the predator versus prey system, where we're going to identify what's happening in the differential equation and then analyzing it afterwards as best as we can. Now, this right here is going to be an example of that situation. Now, note that what we have right here is actually beyond a differential equation. This is what we call a partial differential equation, or PDE, actually, in short. I guess, like, oh man, I kind of really messed up there. Hopefully we don't need that part anymore. So anyhow, so yes, what we're talking about right now is that we're dealing with something called partial differential equation. And what that means is that when it comes to functions that you can take the derivative of, you have a single variable that you have been dealing with so far, but then you might have equations that might have to deal with two or more equations. And so when you take the derivative, we have to take what is known as a partial derivative, and hence that's where we get the partial differential equation from. So here you can see we have two setups right here. We have dr dt and dw dt. Both are going to be functions where their derivatives are going to contain the original equations of not just themselves, but also of the other. So dr dt contains both r and also w, and then also dw dt contains r and also w. So those are considered partial differential equations. So what I would like to do is I want to translate what is happening over here, so then that way you guys could get a better understanding. Now, in terms of, once again, thinking about, okay, is it possible to solve for this? The answer is probably yes, but it's going to take a lot of skill and also a different math course to do so. So that's what we're trying to avoid if possible. Okay, so here's what I'm going to tell you. One of these, not one of these, but this right here is going to represent what is known as a predator versus prey system. Okay, so imagine it as the following. One of these population, R, and what the other population, W, one of them is a predator and the other one is going to be prey. And what I would like to do is I want to think about, like, how they interact with each other and how does this apply to what we're doing so far. Now, looking at my partial differential equation, or PDE for short, you'll notice that I have the slope field on the right-hand side, just so that you can kind of get a better understanding of this. So once again, this is a predator versus prey system. Now, in an ecosystem where you have both predators and prey, what will hopefully happen is that they will kind of, like, mingle with each other. And then you can have, I guess, like, one of three things that can happen. Number one, the predator takes out the prey. So then that means that there's going to be only predators left. Number two, maybe the prey can somehow outlive the predator and just kind of kill him off, which is very unlikely. And then number three is that they all coexist with each other. So that's what we want to consider then. Okay, so either the predator lives in the end, the prey lives in the end, or they can both coexist in the end. So in this scenario, let's go ahead and try to figure out which one's which. Now here, I'm going to note the following. You'll notice that there's a part of the PDE that has both R and W in there. And that right there represents how they interact with each other. So R times W. So that's kind of like the interaction between the two populations. In the case of where one is negative and then the other one's positive, then that basically tells me that one population is going to benefit from interaction, whereas the other one is going to not benefit from the interaction. And well, thinking about how predator and prey actually works, then that tells me that this right here, R, must be the prey scenario, the prey population, because they do not benefit from interaction. But whereas W over here, they are going to be more like the predator in this case then, because when they interact with the other population, their growth is going to increase. This part at the very beginning tells me how the population itself is going to be, but it unfortunately doesn't really tell me too much about if it's predator or prey in this case, right? So, one is R, one is W. So I guess maybe, just to make it a little bit easier, W in this case, let me see, what kind of predator starts with W? Maybe let's say wolf in this case then. And then whereas R might be like, say, rabbit in this case. So that's what's happening for the most part then. So the rabbit normally grows without any kind of problem if it weren't for the predator, because you can see that DRDT normally would be positive if R was just there by itself. But with the interaction with the wolf, then that's where you're losing population. But whereas the wolf, maybe, they actually don't, they need some sort of nutrition resource or something to kind of work off with. And so they normally would die off, and hence that's why they would be considered a predator. So that's the first part. We established that, which one's the predator, which one's the prey according to their interaction. Now, we have to determine what happens over time between these two populations then. Are they going to be able to coexist, or are they going to kill each other off? So in either of the three cases, we're thinking about what happens as time progresses in the very end, right? As time approaches towards infinity, and by the way, all of these equations are a function of time, right? Rabbit population is a function of time. Wolf population is a function of time. So over time, limit as t approaches towards infinity, you're going to basically hit something, right? And that something is going to be kind of like a stable population. Either they all die off where one population is equal to 0, or maybe they can coexist where the population is equal to some sort of finite number. But regardless of which one it is, right, that endpoint, that population is going to be where the population growth is going to be equal to 0, right? If your population dies off, you're not going to have any growth anymore. So dp/dt is equal to 0, or in this case, dr/dt is equal to 0, or dw/dt is equal to 0. Or if you can somehow find out the way they coexist with each other, that means that there's no longer going to be any kind of growth or decay in any way whatsoever also too. And here, if you look at the slope field on the right-hand side, right, remember once again that the slope field is kind of like a pond where you can kind of travel along the current. If I were to, let's say, start over here at some point over here, right, follow the slope field, let's see what's happening over here in this case. You're going to basically kind of circle around like so, and it looks like if I'm looking at it correctly, then that means that this is going to spiral inward like so. What that tells me is that the population of R and population of W, even though one is prey and the other one is predator, they are going to be able to coexist with each other because of the spiraling. If I were to maybe, let's say, graph it out, right, to see what each one of these population looks like over time, let me go ahead and draw that on the side. Let's see as a rough sketch. So here's time for one population. Here's time for the other population. Let's say the first one is going to be for R, for the rabbit then. You'll notice how it's kind of like going back and forth from the left and right, and so forth. And then eventually it's going to move inward. So my guess is that the rabbit population is probably going to go up and down and up and down. But then the oscillation is going to get smaller and smaller and smaller, because you'll notice once again, horizontally, you're going back and forth, but you're getting closer and closer to some sort of equilibrium. Whereas for the wolf population in this case, it looks like vertically, right, because that's where W is, you're going to go up and then down and then up and down and up and down. So just like with the rabbit population, you're going to have some sort of oscillation where they are approaching towards some sort of equilibrium for the population. So then the question is, okay, well, what is that population in this case? How do we figure out where that equilibrium is? So you can probably see it like right here on the graph. Well, as I said earlier, the thing that you can do is look at when dr dt and dw dt is equal to 0, because at the equilibrium, no matter which one it is, the rate is supposed to be equal to 0 then. So I'm going to go ahead and maybe get rid of this guy right here so you can see a little bit. Maybe we can hopefully spend only one screen for this whole session. We'll see how that works out. Okay, so as I said, dr dt, this whole thing, I'm going to go ahead and set equal to 0. So 0 is equal to 0.08 r minus 0.001 multiplied by r times w. And then for the wolf population, I'm going to set that also equal to 0. So 0 is equal to negative 0.02w, and then plus 0.00002 rw. And hey, look at that. After all this time of learning calculus, what you're asked to solve for is not even calculus, but rather a system of equation. So if you can solve for the system of equation of what r and w are equal to, then you're pretty much home free then. Okay. So let's go ahead and do so. The top part, let me go ahead and factor out something. I'm going to go ahead and factor out the r from both of these parts. And I'm going to go ahead and factor out also the 0.001, because I like looking at numbers inside a factor that are going to be nice and whole. So if I factor that out, then what I'm going to get is in the inside, we have 80r, and then we have minus w in this case then. Okay, actually, no, not the r is going to be factored out. So let me go ahead and take that out. So this guy right here is just going to be 80s minus w. And for the bottom part, we're going to go ahead and do the same thing. Maybe what we can do is factor out the big term with a bunch of zeros. So 0.00002, and then we can factor out a w in this case. And what we have left in there is going to be negative 1,000, and then we have plus r in this case. Okay, so those are going to be my factored form. Now, in one case where you can see the factor is r and w by itself, you'll notice that r can equal to 0 and w is equal to 0. And that right there is what is known as a trivial solution, because when both populations equal to 0, that's not really a case that I really care for, right? Because, just because it works doesn't mean I care for it, because, there's nothing to work off of. So we're going to go ahead and get rid of the trivial solution. But the part that I am interested in is going to be the equilibrium part, which will be the factors from these guys right here, which tells me when w is equal to 80 and when r is equal to 1,000. And that right there tells me, hey, that's where it's going to be kind of like that harmonious, I guess, population where the two are going to be able to coexist in. So if there's going to be 1,000 rabbits and then there's going to be 80 wolf, then we're just going to have a perfect ecosystem. All right, well, thank you so much for watching, and hopefully this one is a pretty straightforward lesson. All right, I'll talk to you later. Bye.